Okay, before studying unsymmetric bending, you have to be thorough with symmetric bending of beams. You have already studied symmetric bending of beams in your last semester in elementary solid mechanics course. Now we will have a review of pure bending of symmetric beam. It is necessary to understand this to study unsymmetrical bending of beam. Consider a consider a long beam with a which is having a cross section which has one axis of symmetry. So this cross section is symmetric about the area of cross section is symmetric about this axis. So it is mirror image of this side. So now we know that in the case of beams, beams are the structural members, prismatic structural members, which is loaded perpendicular to the longitudinal axis. Okay. What does that mean? Prismatic members means the cross section is same throughout the length, and in the case of beams, the loads will be perpendicular to the beam. So if you have a beam like this, as shown here, it is the longitudinal axis. So the loading will be perpendicular to the longitudinal axis. Now we will consider this beam. In this case, here we set the coordinate axis, xyz axis. The origin is at one end, that is here we set the origin O, and the y axis is the axis of symmetry. Okay, can you see this here? Same axis is shown here. The y axis is the axis of symmetry, and the x axis is the axis parallel to the length, or it is a longitudinal axis. Okay, we will discuss about the position of this origin later, and just know that the direction of the y axis will be the axis of symmetry, and the x axis will be in the direction of the length or longitudinal axis, and z axis will be perpendicular to both x and y axis. Okay, now so the beam is symmetric about xy plane. Okay, here the x axis is in this direction, and y axis is the axis of symmetry. X axis is in the length direction. So xy plane is the plane of symmetry of this beam. Both sides of the beam will be mirror shapes. Okay. Now we will come to the loading. Okay. Now we draw this xyz axis here separately for better understanding, for clarity. Now the loading, we have to consider the loading. Okay, we know that in the case of beams, the loading will be perpendicular to this longitudinal axis. So the loading will be, if we consider the forces applied on the beams, that will be in this direction, or any direction. But in the case of symmetric bending, the forces will be applied only on axis of only on planes of symmetry. Okay, here the plane of symmetry is xy plane. So the loads will only act on this xy plane. So a general load in xy plane can be in this direction. So it can have an y component, x component, and a y component. But we know that in the case of beams, there will not be any axial force. So there should not be any axial component. So the load will be solely in y direction. The force will be solely in y direction. So the load can be either in positive y direction or in negative y direction. So but in the case of pure bending, we assume that for a beam to be under pure bending, there should not be any lateral loads. There will not be any lateral forces. The bending should be only due to couples moments. So here we will not have any forces. So the only possible load is couple, and the couple will be in which direction? In xy plane, or okay, we'll show the couple in xy plane. The couple can be in which direction? Maybe in clockwise direction, or maybe in anti-clockwise direction. Okay, in the case of bending, we have one sign convention for shear force and bending moments. A positive bending moment will be a positive moment, the bending moment or the couple in the positive direction, which is applied on a positive force, or a couple in negative direction, which is applied on a negative force. Okay, so here this is a positive phase because the normal is in positive x direction. So the couple should be for the moment should be in bending moment should be positive. The applied moment will be moment should be in positive direction. So we have a moment in xy plane that is positive direction. So okay, okay, to find out the positive z direction, we can positive moment, we can use right hand thumb rule. So the moment in xy plane, the direction of moment in xy plane will be z direction. Okay, so we have to place our thumb in positive z direction and just try to rotate the other fingers. So it will be in this direction. Okay, we have to rotate the fingers in this direction. So it is an anti-clockwise moment will be the positive moment. Okay, so here we are applying a an moment m z, that is the positive moment. Generally we show positive moments in general cases. So what will be the moment in this direction? Okay, for this should be in equilibrium, there should be an equal and opposite moment mz. So what will be this direction? This is a clockwise moment in xy plane. Okay, so the moment direction will be in negative z direction, so it should be negative. But in the case of bending moment, since even though the couple is negative, the bending moment is positive. Why? This moment is applied on a negative phase. If we take the normal here, that will be in negative z direction, negative x direction. So this is a positive. In both sides we have positive bending moments. Okay, now we will consider the bending of this beam. And one more thing I have to say, here we use x, y, z coordinate system. Another way to find the direction of moment, if we have a moment in xy plane, so just keep this order. If we have a moment in xy plane, if the moment is starting from or rotating from x to y axis, so that then the moment will be positive. Here it is the anti-clockwise moment will be from x to y direction, so it is positive. Other if from y to negative, so here the order will be changed, not in x y z in this, not in this order. So that will be negative z direction. So in the case of xz plane, for example, in the case of xz plane, if it is from z to x, that will be in positive y direction, otherwise if it is from x to y, that will be in negative y direction. So okay, now we will consider the bending of this beam. Okay, now since the beam is a beam is having a uniform cross section throughout its length, we can show the beam like this. The x-axis is along the length and y-axis is perpendicular to the x-axis, and it is along the axis of symmetry. Okay, and z-axis will be perpendicular to this. Now after the action of due to the action of these two bending moments, what will happen to the body? This will bend, or this will bend in this direction. Okay, can you imagine that? This will bend in this direction. Sorry. Okay, this will bend in this direction. If the moment is in opposite direction, what will happen? This will bend. If the mz and these things are in, if this is in this way, the bending will be in this direction. So since the moments are as shown here, the deformed shape will be like this. Here one thing we have to note, that we always consider small deformations only. Okay, now we have a bending, we have a deformed shape like this. Now we can see that the top portion of the beam, what happened to top portion of the beam? It has been compressed. The length of this has been length will be shorter than this length. Okay, and what happened to bottom portion? This length will be shorter than this length will be shorter than this length, or this length is increased in the bottom part, length is decreased in the top part. Top fibers of the beam will be under compression. And bottom fibers will be under extension. Okay, or under tension. Now there will be, since here the deformation is positive, or length increases, and here the length decreases. So there will be some point here, there will be some fiber here where the length does not change. So if it is some length L is the length of the beam, the length of this fiber will be same, that will be L. Okay, that length does not change. Okay, since due to the shape of the beam, if we have that fiber here, somewhere here, okay, if we have fiber somewhere here, okay, we can say that it will be throughout there will be a surface where the length in this surface the in this surface the length does not along this surface the length is same as the initial length. Top of the surface the length will be reduced and bottom of the surface length will be increased. So here there will be a negative strain here, here it will be positive strain, positive change in length. So this surface above which the length of the beam reduced and below which the length of the beam increased is called a neutral surface. This is called a neutral surface. Okay. Now we have to study one more term, that is neutral axis. Okay, what is neutral axis? Neutral axis is the intersection of this neutral surface with cross section of the beam. So this will be a straight line. Okay, this is called neutral axis of the beam. It can be found if you take any cross section that will make an intersection. If you take an intermediate cross section here, that will take an intersection with the neutral surface, that will be the neutral axis. Okay, I think you got the point. Neutral axis. Now if we consider a small element, say A, B, C, D here, that will deform like A dash, B dash, C dash, D dash here. Okay, now we will consider an element A, B, C, D. Here this element A, B, C, D, this element, and due to the application of these moments or due to pure bending, the shape of the that element changed to like this, and the length AC was shortened to A dash C dash, and the length BD was increased to B dash D dash. Okay, now we will study the deformation of that element in detail. Okay, here we have the undeformed shape of the element ABCD, and this is the shape of the element after bending, that is the deformed shape. Okay, before bending, the element has a length of delta x, and n is the neutral axis, and EF is a line which is y distance away from, S is a longitudinal fiber which is y distance away from the neutral surface. A C, these are the outer surface, AC and BD are the outer surfaces. Okay, now after deformation what will happen? Since this is of very small distance delta x, we can assume these curves represents the arcs of a circle. Okay, so B dash D dash is an arc of a circle, and N dash will be arc of another circle, E dash F dash will be arc of another circle, A dash C dash will be arc of another circle. In this way we will do the okay, these all these things are arcs of circles, and we can also see that these A dash C dash, B dash D dash, N dash E dash F dash, all these lines forms arcs of concentric circles. That means all has same center. Okay, all has same center, that is here. So we define the radius of curvature from, it is a distance from center to the neutral axis, center of curvature to the center of the arc to the neutral axis. Okay, so what will happen to this element, each element? Here BD was having length delta x is deformed to B dash D dash. What will happen to this? The length will increase. AC will be deformed to A dash C dash, the length will be decreased. And same in the case of EF. EF having delta x length is having another length, that is E dash F dash. In this case length is decreased, and in the case of neutral axis length is same as delta x. Now in the case of neutral surface the length is same as delta x. Okay, now I am going to write the length of this thing is delta x, and now we are going to consider we are considering the deformation of element EF, this line EF, that is changed to E dash F dash. So the length will be reduced, that we know. So we say that is the new length is, say it is delta x dash. Now from this diagram we can write delta x is equal to, what will be delta x? If delta theta is in radians, we can write delta x is equal to r into delta theta. Okay, the layer EF is y distance away from the neutral layer or neutral surface. For small deformations, even after bending, the distance of the layer from neutral surface does not change. Here also it is y. So radius of the arc E dash F dash will be this distance is y. So the radius of the arc E dash F dash will be r minus y. Okay, so we can find the length of the arc as delta x dash is equal to, the radius was r minus y, and the included angle is delta theta itself. So this is the new length of, this is the changed new length of the element. Previously it was delta x, every element was having delta x length. Now it is delta x dash, which is r minus y into delta theta. Now we can find out the strain, that is normal strain in the layer, in this layer. Okay, so normal strain can be written as changing length divided by normal strain, can be written as strain. So here this is in the direction of x. Actually the x axis was in this direction and y axis was in this direction. So this is in the direction of x. So the strain can be, normal strain will be the normal strain in x direction. So we take an arbitrary layer which is y distance away from, the y is not fixed, we can change y. So it is not a fixed layer. So for any layer which is y distance away from the neutral layer, we can find the strain or normal strain in x direction, such as change in length divided by original length. The original length is already, it is delta x, it was originally delta x for all layers, and after bending the length changed to delta x dash, and that new length minus the original length will give the change in length. So we will get epsilon x is equal to we have delta x dash is we have here r minus y into delta theta, and it is delta x was r delta theta, and it is here also r delta theta. So this will give epsilon x is equal to minus y by r. This gives the strain of any layer y distance away from the neutral axis. Okay, if we want to find the strain in a layer which is some, if we have d distance, if we want to find out the strain in this layer AC, previously it was AC, now it is A dash C dash. So we have to give this distance instead of y. Why this negative sign? The negative sign is due to the nature of bending. Here the y direction, if we take y in positive direction, that is in upward direction, here y is given as positive direction. So if we go upward from neutral layer, each layer will be compressed. Okay, so that means the strain has a negative value. Okay, the change in length is negative, so the strain will be negative. So if we go downward from neutral layer, that is in negative y direction, what will happen? It will be extended. So we will have a positive strain. Now we can calculate normal stress in x direction. Here we assume only stress is sigma x. All other stress components are 0. So here we can write sigma x as E into epsilon x. That is Hooke's law, where E is the Young's modulus. So from the previous equation we can write, we know the value of epsilon x, we can write minus E by R into y. So this is the stress at any point which is at a distance y from the neutral surface. So this will give you the normal stress in the beam due to bending. Here we can see that E is a material constant, and R is the radius of curvature, and for a specific bending the R does not change. So we can find that we can say that the stresses vary linearly with the distance from neutral axis. So at neutral axis the stresses will be 0. So above the neutral axis, here we have a negative sign. Above the neutral axis we will have a negative stress or compressive stress, and below the neutral axis we will have a positive or tensile stress, and the variation will be, if we take the cross section like this, if this is the neutral surface, so we can, the variation will be at neutral surface, the variation will be like this. Here it will be compressive loading, here it will be tensile loading. So it is a linear variation. Now where will be the stresses, where the stresses will be maximum? The stresses will be maximum at a point which is farthest from the neutral surface. Here we have this point is the farthest point. So if it is D, we can write instead of y we can put d, and we can calculate the maximum stress.